In this video, we're going to get some practice using the comparison test and the limit comparison test. In both cases, the idea is to compare a given series with a series that is known to be convergent or divergent. Most of the time, the series we will choose for comparison will be a p-series or a geometric series. The comparison test requires that we deal with series involving positive terms only. The first part says that if we have a series whose terms are smaller than a known convergent series, then our series is also convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then that original series is also divergent. Determine whether the series is convergent or divergent. Part A, the sum n equals 1 to infinity of 7 over 2n squared plus 5n plus 9. First, we notice that all terms are positive, and we want to come up with a series to compare this to. When thinking about a series for comparison, we're going to focus in on the dominant term. In other words, for large n, the n squared term is going to be the dominant term. So we're going to compare with the series 7 over 2n squared. Looking at the term-by-term comparison, we have a sub n is always going to be less than the corresponding terms of our comparison series, like this. Now we consider the convergence or divergence of our comparison series. Which is a convergent p-series where p is equal to 2, which is greater than 1. That means our original series is convergent by the comparison test. Part B, the sum n equals 1 to infinity of the ln of n over n. Again, notice all terms are positive. Here we will compare with the harmonic series, which we know to be a divergent series. Looking at a term-by-term comparison, we take the terms of our given series and notice that the numerator is going to be larger than the numerator for 1 over n whenever n is greater than or equal to e, but of course n has to be a natural number or a positive integer, so anytime n is greater than or equal to 3. Recall that the ln of e is equal to 1, so the ln of 3 has to be greater than 1. Now, since we know that the harmonic series diverges, and the terms of our given series are larger than the corresponding terms of the harmonic series, our given series must also diverge. Part C, the sum n equals 1 to infinity of 1 over 2 to the n minus 1. Again, notice all terms are positive, and it seems reasonable to compare this to the series 1 over 2 to the n. We recognize this as a convergent geometric series. But we run into trouble when we do our term-by-term comparison. The terms of our given series are actually larger than the terms of our comparison series. So the fact that our comparison series converges does not help us establish that our given series is going to converge as well. So instead, we're going to try the limit comparison test. For the limit comparison test, again, we need two series with positive terms. If we take the limit as n goes to infinity of the ratio of their nth terms, and find that this gives us a constant, a finite number that is greater than 0, then either both series converge or both diverge. So let's look at the limit as n approaches infinity of a sub n over b sub n. We can rewrite this limit by multiplying top and bottom by 1 over 2 to the n. As n goes to infinity, this expression approaches 1, which is greater than 0. Now, applying the limit comparison test, either both series converge or both series diverge. But as we saw earlier, our comparison here is a convergent geometric series. Therefore, our given series is convergent by the limit comparison test. Part D, the sum n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the fifth. Again, notice all terms are positive. We're going to focus here again on the dominant terms. So in the numerator, our dominant term is 2n squared, and in the denominator, we have n to the fifth, but it's under a square root. In other words, we're going to compare with two n squared over the square root of n to the fifth. Rewriting this, we have 2 times the sum, n equals 1 to infinity, of n squared over n to the 5 halves. This simplifies further, and we recognize this as a divergent p-series, because p is equal to 1/2, which is less than 1. Since a term-by-term comparison of these two series is going to be kind of complicated, let's go ahead and try the limit comparison test. So we're going to take the limit as n approaches infinity of the ratio of a sub n and b sub n. We can rewrite the quotient a sub n over b sub n as a sub n times the reciprocal of b sub n, which will be n to the 1/2 power in the numerator and 2 in the denominator. Rewriting this, we have 2n to the 5 halves plus 3n to the 3 halves over 2 times the root 5 plus n to the fifth. Now we'll multiply by 1 over n to the 5 halves on top and bottom, like this. In the numerator, we have 2 plus 1 over n, and in the denominator, we have 2 square root of 5 over n to the fifth plus 1. As n goes to infinity, the numerator is simply 2, and the denominator is 2 times root 1, which is also 2, which is equal to 1, which is greater than 0. By the limit comparison test, that means that both series either diverge or converge. And since we already saw that our comparison series was a divergent p-series, that means our original series also diverges. Part E, the sum n equals 1 to infinity of n plus 1 over n times 2 to the n. Once again, notice that all terms are positive. Looking at only the dominant terms, in the numerator we have n, and in the denominator we have this term here, n times 2 to the n. So with that in mind, let's compare with the series 1 over 2 to the n. We know this series to be a convergent geometric series. We could rewrite it this way. It converges because r is equal to a half, and of course absolute 1/2 is less than 1. So now we take the limit as n approaches infinity of a sub n over b sub n. We can rewrite that quotient as a sub n times the reciprocal of b sub n. And this, of course, simplifies to n plus 1 over n. And that limit is equal to 1, which is greater than 0. So once again, by the limit comparison test, either both series converge or diverge. And because our comparison series is a convergent geometric, both series converge. Part F, the sum n equals 1 to infinity of 1 over n factorial. Once again, notice all the terms are positive. Also, let's notice that n factorial, which can be written backwards like this, n times 1 less than n times 2 less than n times all the way down to 3 times 2 times 1 is going to be greater than or equal to 2 times itself n minus 1 times. The reason we have n minus 1 multiplications here is because if we look at this side, we have n minus 1 factors here when we disregard this 1, which clearly doesn't change that product. Noticing this allows us to compare the given series with the geometric series 1 over 2 to the n minus 1, which we know to be convergent, because r equals a half, and of course the absolute value of a half is less than 1. Now if we do a term-by-term comparison, we have a sub n is equal to 1 over n factorial, and we want to be able to say that these terms are less than or equal to 1 over 2 to the n minus 1, which is our b sub n. Let's compare some terms and see if this is true. So a sub n is going to equal 1 when we plug in 1. We're going to get 1 over 2 when we plug in 2. 1 over 3 times 2 times 1, which is 6, 1 over 4 times 3 times 2 times 1, which gives us 24, and onward like that. Whereas b sub n is equal to 1 when we plug in 1, 1/2 when we plug in 2, 1/4 when we plug in 3, 1/8 when we plug in 4, etc. And we notice that the terms for a sub n are indeed smaller than those for b sub n when n is greater than or equal to 3. Therefore, our given series converges by the comparison test. Go ahead and do the remaining problems on your own. The trickiest part is usually determining which series to compare with, but remember, if you usually just focus on the dominant terms in the numerator and denominator, that should guide you to a familiar series for comparison.